자, 그럼 오늘은 디스카운트 팩터와 베타 프라이싱 모델의 연관성에 대해서 좀 자세히 보도록 하겠습니다. So today we will study about the relationship between discount factor and beta pricing model. 자, 첫 번째 이퀘이션을 볼게요. 이 이퀘이션 많이 봤죠? So the first equation says the pricing is expected value of stochastic discount factor times m. So the stochastic discount factor should price all the assets whose payoff is given as x. Then we also have seen that the excess return, expected excess return is just sum of the gamma plus beta times lambda. And how did we derive this from the basic pricing equation? And we decompose the expectation of the product into covariance between m and x, and the expectation between expectation of m times expectation of the payoff. And then we use the fact that risk-free rate is 1 over expected value of m, and divide both sides by the price, and then you get the expected excess return in terms of the beta times lambda, where beta is given as the covariance over variance. So this is the usual regression coefficient of the individual returns on the stochastic discount factor. And lambda m, which is the price of risk. Okay, this is the price of risk, is given as the negative of variance of m divided by expected value of m. And we saw in the consumption-based model, the stochastic discount factor can be expressed as the beta times the consumption growth to the power of gamma. So here implicitly the utility function was assumed as right. So that was the assumed utility function. Okay. So the fact that beta is given as the covariance over variance means that the beta is the time series regression of beta. So what do I mean by that? So beta is the covariance of the return on with stochastic discount factor divided by the variance of m. This means that m is the regression coefficient of regression of the return on m. In other words, if you have return I, you regress it on the stochastic discount factor using this time series regression. In other words, you fix I and use time series relationship, and then you get beta I. You should have beta I here, okay, and that's basically the expression given above. So from the time series regressions, you get betas for each stock or each portfolio. So I can be a stock or a portfolio. Okay. So you get beta from the time series regression for each asset I. And once you obtain these betas, then you run the second stage regression, What is the second stage regression? You regress the expected return on each asset I on betas. And then that cross-sectional relationship is going to give you two things. The first one is the slope on beta, that is, which is lambda m, the price of risk, and also the intercept. The intercept should be gamma, or that is risk-free rate. Okay. Now, in this particular case, where the factor is just a stochastic discount factor, in other words, in this case where we use m as the factor, or we use the regression coefficient on m as beta, in this case, lambda is expected to be negative. Why? First of all, we see that from this expression. The first reason why, so y is gamma negative. The first reason is that if you look at the expression, so mathematically, this is negative number. The numerator is positive, and variance of some number is always positive, and the denominator is also positive because denominator is just 1 over risk-free rate, and risk-free rate is positive. So lambda, because of the negative sign, mathematically is negative. The second reason is that the price of risk for m should be negative. So what's the meaning of that? If some asset has high beta with respect to m, okay, well, if some asset has high beta, that means that asset I is going to pay when m is high, right? This m is going to pay, in other words, the return on the asset, and m is positively correlated. In other words, the covariance between Ri and m tends to be positive. Okay. What kind of asset is this? What kind of asset? What kind of asset is going to pay when m is high? High m state, when m is high, that means it's a bad state. What kind of asset is going to pay when the state of the world is bad? It's an insurance. And investors want to have these kind of assets even when the expected returns are low, right? So these are the assets that pays you well. Okay? So these are the assets, even with lower expected returns, you want to hold. In other words, if there's an asset, so if asset I has negative beta, if asset I has positive beta, beta is positive, that means beta times lambda is negative. Okay. In other words, that asset should have excess return negative, meaning that assets, this is the excess return on asset I, that asset I's return should be lower than the risk-free rate. Okay, so if the asset works as an insurance, if there's an asset that pays off well when the state of the world is bad, investors want to hold such assets even if the expected return is lower than the risk-free rate. And that is the reason why the price of risk for M should be negative. Okay. So the stochastic discount factor gives us a very natural expression for the beta pricing. But there's one problem with the stochastic discount factor. In the previous case, we used a consumption-based model. In other words, we used the consumption data. For consumption data, like any other macroeconomic data, are available only in low frequencies and they lack in time. Therefore, we want to use something that can proxy macroeconomic data or like consumption growth by using this technique. So we will project the stochastic discount factor or consumption growth or marginal utility on the payoff space. So we will use the return data or we will use the financial data to proxy the stochastic discount factor that we call projection. Projection is simply the linear regression. So we are getting the linear combination of payoffs that can proxy the stochastic discount factor very well. So how do we do that in practice? So suppose we have n basis assets. These n assets are the basis. So they form the basis for the payoff space. So we are basically assuming that these assets will spend the asset space very well. And then we will regress the stochastic discount factor on X, meaning that M, stochastic discount factor, is going to be expressed as a linear combination of these n different basis assets from some and some epsilon, where the epsilon is assumed to be orthogonal to the payoff space or the basis assets. In other words, we are regressing stochastic discount factor on the basis assets. And then mathematically, what do you get? Mathematically, okay, how do you back out B from here? So you multiply X prime on both sides. Okay. And then to back out B, what do? You multiply X prime inverse on both sides. And then you will back out B plus epsilon times X prime X inverse. And then if you take expectation on both sides, and we know that expectation of this thing is 0 because epsilon is orthogonal to the payoff space. Therefore, we get B in this fashion. And that is the projection of M on X or linear regression of M on X. Okay. And the projection is obviously B times X. Now we can convert X prime, I mean the X prime now should be B prime X. Okay. Now we can convert X prime into returns because returns are much easier to deal with than prices. So how do we obtain returns? We divide by prices. What is the price? Let's just suppose price is given like that. So it's the price. So that is the price function of some asset with payoff X star. Now, from the stochastic discount factor, we know that this should hold. And we also know M can be expressed as the projection and the idiosyncratic payoff times X prime. And this is basically this. And then we know this term is 0, so we get this. Okay? So, and then we get return as the payoff divided by the price, where the price is given as here. And this R star is called a factor mimicking portfolio of M. In other words, how do we get a factor mimicking portfolio of some payoff? Of some stochastic discount factor? You first regress the stochastic discount factor on the basis assets and the linear combination of that basis assets, or linear regression, is the factor mimicking portfolio. Now, using the factor mimicking portfolio, you can do the same math and then get this expression. Okay, how do you get that? There are many ways. The easiest way will be m times r. This is 1. Okay. Now m. Okay, and then you plug it in and then use the same techniques and you can get this. Now, the gamma of so this is gamma of R star. Okay, R star is some factor mimicking portfolio for the stochastic discount factor. So R star is given as like this, okay? And more precisely, it is going to be like that. And the sign is, again, a negative number. Okay? And the sign is the negative number. So and the reason is same as before, because this factor mimicking portfolio co-varies positively with the stochastic discount factor. So if the asset, so when R star is high, it's a bad state of the world, and R star is low, it's a good state of the world, right? Therefore, the price of risk associated with R star should be a negative number. Okay, and this is negative because the expected return on the R star.
Okay, here's what I found.
Oops. Okay. So the reason why the gamma is negative is same as before. Okay. And why is gamma R star given as expected value of R star minus lambda? You plug, because this pricing equation 1 should hold for all the assets, so it should also hold for R star as well. So more generally, you have gamma plus beta lambda R star. Now, this should hold for when I is the factor mimicking portfolio, and you have E of R star minus gamma should be the lambda of R star. Okay? So that is the usual technique to get the factor risk premium when the factor is a traded portfolio, like in this case of the factor mimicking portfolio. We are now extending the model to the multi-factor case. So in the previous case, we assume that M can be just expressed as a one factor. Okay. I mean, if you can find a one single portfolio that can mimic, that can proxy the stochastic discount factor, then the world will be a one factor case. But it's also possible, I mean, it's more likely that it's more likely that the stochastic discount factor can be proxied as some multi-factors. Okay, so F, I would say, is a K factor, then this is going to be a K factor model. So stochastic discount factor summarizes the good and bad state of the world. And it is more likely that investors care about multi-factors, not just one factor, to describe their marginal utilities. If their marginal utility or marginal value depends on multi-factors, it's more likely that the stochastic discount factor is described by K factors, like in this case. And we will assume that the expected value of the factors is 0 because that makes the calculation easier. Now, with the multi-factor, we can do the same pricing we can use the same pricing formula as before. So expected value of the excess return times the M is 0. Okay, so that's the usual pricing equation. And then we can decompose this expectation into covariance between excess return and M plus the expectation of the two things. Okay, and then we get this, and we get that by plugging in M equals A plus BF. Okay. In other words, it's covariance between RE and A plus BF plus E of RE, because we normalized to make expectation of the stochastic discount factor to be 1. Okay. And then within the covariance parameter, this constant goes away and constant B can come out, and this is what we have. Okay. And then here's a trick. We will multiply variance of F and divide it by the variance of F. Why do we have the matrix notations? Because variance of F is a K by K matrix, where we have the variance of vectors in the diagonal elements, and the off-diagonal elements are the covariances. And this term here, okay, the covariance times variance of epsilon, this is again the regression coefficient, or this is beta. That is the beta for the multi-regression case or multiple regression case. So beta is the multiple regression coefficients of excess return on the factors. So in the first stage, you do the time series regression of excess returns on F, and you will get beta. The beta is a K by 1 vector. Once you have the betas, then you can describe this cross-sectional relationship using the beta pricing model. Okay. And lambda is given in this fashion. Similarly as before, similar to the one factor case before, we can use the factor mimicking portfolio, because using traded assets or returns instead of macroeconomic data is much more convenient in many cases, because again, traded assets are available in a higher frequency. So say factors are not returns, but based on macroeconomic variables, then it's easier to project them on the payoff space in practice. So how do we do the projection? It's the same as before. We do the linear regression, right? Now, once we have the projection of F on the basis X, basis assets X, this projected animal, the projected part of the factor carries the same pricing information as the full stochastic discount factor. So we can instead use the projection, okay, the projection instead of the full stochastic discount factor, and then we can obtain the same multi-factor pricing model. Okay, so in practice, it's much easier to work with returns. So how do we get returns on the factor mimicking portfolios? We divide by the price of the factor mimicking portfolio. And you should also note that when you project on the payoff space, you shouldn't project on the return space, because return is not a space. Return doesn't have a constant. So mathematically, regressing on the return doesn't have a very good property. So it's better, it's much better to work with the excess returns because excess returns is a space because it has constants. In other words, if there's an element in the excess return space, okay, if there's an element in excess return space, say there are two elements, R1, I mean excess return 1 and 2, and then any linear combination of is again in the excess return space. Okay? But the return doesn't have this property because say there's a return A in the return space. That doesn't mean that A times some constant times return is going to be in the return space. That doesn't hold. I'm sorry. This is not true. So how do you do that? Basically, you form basis assets using excess returns and then regress the factor mimicking portfolios, regress the macroeconomic variables on the excess basis assets from the excess returns, then you will get the factor mimicking portfolio.